Welcome back, everybody. Today we are going to be analyzing changing mass. So that is wrong thing. There you go. Alrighty. Changing mass. Alright, so let's analyze a mass traveling on the x-axis subject to 0 external forces. So since we are restricting ourselves to the x-axis, we have one particle. We're just going to denote that one particle as having a mass m, and v, which is going to be the velocity in the x-axis, and it'll also have a direction. So hopefully that will make sense. And we are going to assume that the mass is changing. So if the mass is changing, then we're going to apply the product rule, and we're going to distribute that in order to get these two terms. As you can see, if the mass was constant, then the derivative of the mass would just be 0. And therefore, this term would go away, and we're just left with our familiar force term. And we did say that it was subject to no external forces. So the derivative of momentum is, there you go. That was weird. But it's subject to no external forces or any forces of that kind. So that this whole thing is going to be 0. And we are going to move that right term, left term to the right, sorry. And so here we have our familiar force term, and on the right we got m dot v. So even though there are no external forces on the system and there are no other particles, so there is really no interaction forces, the particle certainly behaves as though it is subject to a force. You can see, so we have the force is equal to some kind of acceleration here, and it depends on how the mass is changing, which is certainly really weird. So what we're going to do in this video is analyze what this equation really is saying, and from here on out we are going to be assuming that the derivative of the mass is always going to be less than or equal to 0, because although you could think about it gaining mass in some way, everything that we're going to do from here on out is only going to make sense if the mass is less than or the changing mass is less than or equal to 0. In other words, we are losing mass in the particle, so we're throwing it away somehow. And how we throw it away is going to be quantified in something called a thrust force. You can see that if the changing mass is less than or equal to 0, and that would mean that this right here is going to be less than 0, right? And it's going to cancel out by that negative. That means the force is going to be positive. At least it's going to depend on the sign of the velocity. So if the velocity is positive, it's going to have a positive force, and the velocity is negative, is going to have a negative force, which is certainly interesting. So my goal is to be showing you how it can also be interpreted as how fast the particle is throwing the mass out and in what direction. So in the future, we'll sort of denote direction like this. So we'll bring the negative sign here, and we'll see that this can kind of be extended as a vector, because that negative sign will denote direction. So let us consider the mass before and after it spews out a tiny little bit of the fuel. So let's just analyze an object, for example, like a rocket. This would make the most sense. So here we have a rocket, and it is filled with some fuel, whatnot, and it's going to be spewing that mass out at some velocity. And so maybe this will be a little easier to visualize if I draw something like this. So instead of a rocket, let's just think of something very abstract like a square traveling at some velocity v, and it has some mass m. So let's consider the momentum before and after it spews out a tiny little bit of mass in an instant. So we're going to be thinking about differentials. We're going to be working with the differentials in a way, and we're going to see like how velocity changes in relationship to how the mass changes and stuff like that. So let's just consider the momentum before, which is pretty easy. So that's going to be just mass times velocity. And then let's consider it after. So let's say it kind of threw out a little chunk of mass here. like this. So then it's going to be traveling at a new velocity, v plus some dv, some little change in velocity. And then the mass is going to change by a little bit as well. And it's going to be m plus dm. You may be wondering, why am I adding dm if we clearly are losing mass? And that's because of the condition that m dot is always less than or equal to 0. You can think of dm as being equal to m dot times dt. And so as you can see, if m dot is always less than or equal to 0, that means dm is always going to be less than or equal to 0. So this dm quantity is actually negative. So keep that in mind. It is always going to be negative. This is why we made the condition, because it wouldn't really make sense to be gaining mass, right? We're throwing out negative mass and we're somehow gaining mass. It wouldn't really make much sense. So by that logic, this must mean that this is negative dm. Remember, dm's negative, so this negative, we'll just cancel out that negative, and this whole quantity will be positive. And we also are going to make it negative just so the total mass will stay conserved, right? So if we add the mass of that little bit of fuel, and then we add the mass after it throws out the bit of fuel, you can see that it's just going to be equal to m. These dm's are going to cancel. So that's very important. We are going to assume conservation of mass here. Cool. So then we're going to quantify the velocity of this dm here. So let's say relative to the object or the rocket here, whatever you want to think of this as, it's going to toss fuel at some exhaust velocity, and we'll denote that with VEX. So relative to the rocket. So what we're going to do is take whatever velocity it was traveling at, and then we're going to subtract that exhaust velocity. And this is so we get the speed relative to us, because this exhaust velocity is going to be relative to the rocket. So I want you to think about, if this doesn't make sense, think about if the exhaust velocity was equal to the velocity it was traveling at. So it exactly cancels the velocity, right? So then this VEX will equal to V, and that means this will just equal to 0. Then that would mean that this would be at rest to us, because if we were traveling at V and we toss something in the exact opposite direction, at that exact same v, it will cancel out our velocity relative to some, I don't know, ground observer, and it will appear to be standing still. But relative to the rocket, it will be traveling at negative. The mass will look like it will be traveling at v. So this is why we're going to take v and subtract the exhaust velocity, because this is going to be the relative velocity to us. All right, sweet. So then what we do is just write the total momentum after it throws out that bit of mass, which is obviously a little more complicated. So what we're going to do is just take the momentum of this first, the rocket. It's going to be m plus dm, v plus dv, the new velocity. And then of course we're going to have to add the momentum of the little bit of fuel. And we're going to say that this has to be conserved. mv has to be equal to all this. So we take the velocity of this little bit of fuel, and we multiply by the mass, which is going to be negative dm. So what we're going to do is just set this to equal. This would be the P initial, and this would be the momentum final. So in this case, system's isolated. It's just one particle. Obviously, momentum has to be conserved. So that's what we're assuming, and that's what we're going to take advantage of in order to see what's going to happen, I guess. So if we multiply all this out, I'm just going to write everything out. We're going to get mv, so just the binomial product, m plus or m times dv, and then we're going to get dmv, and then we're going to get dm dv for this term right here. And then here we're just going to do minus dmv plus dmv exhaust. There you go. So that's going to be all the terms expanded, and we can see that cancels. This is going to cancel, and this right here, this term is a second order differential. So if we're taking the differentials to be very, very tiny, right? Very, very tiny changes in mass, very, very tiny changes in velocity, we're looking at these instances in times pretty much. So we're going from some time step to, we're going from some time t to some time t plus dt. So a very tiny time step. And in that very tiny time step is gonna, all the quantities are gonna change by a very small amount. So this would be a second order differential. And we can just say that that's equal to 0 because it's going to be incredibly small, especially if we're taking a first order approximation. But it's not going to really be an approximation with the differentials. They are exact. They're very interesting quantities, very interesting, very weird. You can watch 3 Blue 1 Brown's video on calculating derivatives by kind of working with differentials and geometry and stuff like that. It's very, very interesting. But yeah, so we'll just take that to be 0. And what we're going to be left with is going to be m dv plus dm v exhaust is equal to 0. So now what I'm going to do is just divide both sides by dt, and we're going to shift some terms around. So here we're going to get m dv over dt, which is just the time derivative velocity. And on the right hand side, we're going to get dm over dt, which is going to be the time derivative of mass times the exhaust velocity. So here we have it. We have the final equation, which is known as the thrust force. So this term is the thrust force. As you can see, the left side is force, right side is thrust, and it tells you how much force there is on the rocket, depending on how fast you're throwing the fuel out and by how much fuel you're throwing out. As you can see, it is remarkably similar to what we derived here using the conservation of momentum pretty much. The time derivative of momentum is equal to 0 with changing mass. And this is very interesting because of how similar it looks. And this one is much better because we've just proven that V exhaust can be virtually anything we'd like, and this equation still applies. But that wasn't entirely obvious from this. We couldn't just say that this is just equal to the exhaust velocity and we're done. We actually had to go through some steps and prove that this is indeed true. As you can see, we can set the exhaust velocity to whatever we like. And if we just set it to match the velocity that we're traveling at, then you can see that we just get this equation, and we get that the total momentum is conserved. Which is very interesting, right? Because there is actually a really nice physical interpretation to it. So if we did match the velocity here, like we did just to show you, to clarify like how the relative velocity works and everything like that, if this was just 0, right, the velocity was 0 relative to us, it would carry 0 momentum. But that means this would still carry all the momentum. It wouldn't transfer any of the momentum to the little bit of fuel here. So in that case, the momentum would be conserved. And it's only conserved if the exhaust velocity matches the velocity that is traveling at, which is certainly very interesting. However, not very useful because in general, like for rockets and stuff like that, we're going to be throwing fuel out at a constant rate, at a constant VEX. So a lot of times you're just going to take this to be constant. However, you can do it, you can choose it to be whatever you want. It could be a function of time. So you can say that maybe it could be a step function, like let's say you're doing a really big burn in space and then you're doing a very light, small burn, like a correction burn or whatnot. You can account for that in the exhaust velocity. So there you go. So one more thing we're going to do is naturally extend this to be a vector. So as you can see, we are taking the exhaust velocity to sort of be the magnitude. And this negative sign can kind of come in to denote direction. So as you can see, if we can think of this as a vector pointing to the left, right? It has a magnitude VEX, and the negative sign denotes the direction. You can think of this as the direction it is spewing the mass out, and the magnitude gives it the speed at which we are spewing the mass out. So naturally, I'm going to write this in red. This is the big important equation here. So we can extend this naturally. So this is going to be, the left side is going to be the force of the thrust. And on the right side is going to be m dot d ex. And there you go. This would be the thrust force. So this this vector here, let's say we had a rocket, right? So this Vector would denote the direction we're spewing the mass out, and the magnitude would be the speed at which we're spewing it out. And you can just add this equation to whatever you'd like. So, for example, in the next video, we're going to be going over an example of a rocket-propelled car on wheels, subject to quadratic air resistance. But for this rocket, for example, you could say that the net force on it would be the thrust force. Or how about we just write it like this? So we can just add the thrust force to whatever system we're looking at if it's spewing out mass, which is really cool. Because then we can just add other forces that are important, like the force of gravity and the force of air resistance and whatnot like that. So this is certainly very useful for maybe computer simulations if you're building a rocket game or something like that, like Kerbal Space Program. But yeah, this equation is very fundamental, very useful for rocket propulsion. And knowing this knowledge, I think that counts as you being an official rocket scientist. So take that as you will.